Hello everyone. This video I'm going to talk about the example of Newton's second law. Okay, and I use this Ed Wood machine to demonstrate to do the demonstration. Okay, this is a very typical Ed Wood machine. Okay, there is a, a trolley or pulley here, and there is a rope connect to the two objects A and B. Okay, this is the initial setup of Ed Wood machine. And the mass of A is 4 kilogram and mass of B is 2 kilogram. So you will see that this is the initial setup. And initial setup and A is 30-meter away from the ground. So that's the initial setup. So okay, intuitively the A has larger mass than B. So after this initial setup, A will goes down and B will goes up. And the question asks when A and B reach the same height. Okay, so this we can use the Newton's law to solve the problem, and it also connect to the kinematics 1D kinematics. Okay, and so for this problem we may try to make the problem simple. Okay, so we ignore the mass of the rope. Yeah, actually, yeah, sometimes reasonable assumption because maybe it's possible your mass A and B, the mass of A and B is way much larger than mass of rope, so we can treat the mass of rope, ignore that, okay, and we ignore the friction between the machine and the ropes. That's not that realistic, but we just assume that. Okay, so and also we ignore the mass of the Ed Wood machine. Okay, and also we assume it's constant acceleration motion. Like I say, after the initial setup, the A will goes down and B will goes up, and we assume it's constant acceleration motion. So assume constant acceleration motion, constant ACC motion, constant acceleration motion. Because if A and B is not A and B if A and B do not have the same acceleration, I think they will separate apart or something. Okay, yeah, that means they are subject different force. So that will that will cause some problem. Okay, I think they subject the same force, especially the force from the. Yeah, they must have the same acceleration. If you don't have the same acceleration, yeah, it will cause some problem. Okay, let's just make this assumption. Okay, we don't want to discuss it in very detail. Okay, this is just a practice. Okay, so for this problem, we have to draw the diagram on each object. Okay, so we have to do analyze the force diagram on A and B. So let's start from A. Yeah, let's just treat A as an object. As a point. So the A is subject to the gravitational force. So the gravitational force is ma times the acceleration of gravity, mag, and it feel the tension. Okay, tension from the rope. And like I say, it goes down. Okay, it's moving downward, so its acceleration goes down. Okay, that's for A. And also we do the similar thing to B. Okay, this is a B. And B, yeah, it also subject to the weight. Okay, the weight, MBG, the force, gravitation force, and also subject to the tension. Okay, the only difference is he's moving upward, so its acceleration is pointing up. Okay, and so in this system, we set up the coordinate. Yeah, we set up coordinate. Coordinate is very important. Okay, let us set up the coordinate. Okay, the coordinate we make the okay, it's called y. X, is that necessary? Yeah, that's not necessary. Okay, we don't have to write the Y here. Okay, let's just direction and point upward is positive and point downward is negative. Okay, positive, negative. I think that's enough. Okay, so let's write down using a Newton's second law. What the Newton's second law tells us is it tells us the net force equal to mass times the acceleration. That's Newton's second law tell us. So let's apply this law. So the vector sum or net sum force for object A is, yeah, be careful. The vector sum, the net force on A is, because T is pointing up, so that's why it's positive. I should use the black. Maybe black is better. Okay, T is point up, so it's positive, and the ma times g, the weight of A, so it's point down, so it's minus ma times g, and it's equal to mass of A times its acceleration. Okay, for acceleration, be careful, it's minus A, it's minus A, it's minus A, because it's because the acceleration going down, so it's negative. So you have to be careful with be careful to this negative sign, because if there is no negative sign here, you cannot solve the problem. Okay, so and then we apply the Newton's second law to this object B. Okay, vector sum is, okay, tension goes up and the weight goes down, so it's negative mb times g. Okay, and equal to mb times a. Okay, so and a is positive. Okay, because a goes up. Okay, we list these two equations. Okay, so let's go back to the problem. The problem, what's the problem? What's he's going for? Okay, he want to us calculate when A and B reach the same height. So A moving down and B moving up. So when A and B reach at the same height, actually it's a kinematics problem. Okay, so it's a kinematics problem. So we have to write down the equation of motion. I write down the mostly I favor the equation of motion. I favor xf equal to xi plus vi times t, plus 1/2 at squared. So in this equation of motion, okay, let us check. Do we have initial position of A and B? Yeah, we have initial position of A and B. We have. Okay, we have. And the final position, yeah, we don't know. But that's what we want to solve. Okay. Just leave this there. Okay, so do we have initial velocity of the? Do we have initial velocity of? We have this. Do we have initial velocity of the A and B? Yeah, we have, because at initially this is the A and B are at rest. They didn't do any motion, so they didn't do any motion. That means their velocity are all zero. So we have this. Okay. And T, I don't know, because that's what we want to solve, right? Okay. And the last one is, do we have any information of acceleration? No, this problem didn't give us any information of acceleration. But if we really want to solve the problem, we need to get the acceleration. Okay, or there are too many unknowns, so we have to figure out what the A is. So where can we get the A acceleration? So we can get the acceleration from these two equations, right? Because if we can substitute the T, okay, from this one, okay, let's solve the, let's try to find the A. Find acceleration. I think if we find acceleration, this problem is almost solved. Okay, so here, what do we get? we can have this. The tension is equal to MAG minus MAA. Okay, tension, and then we substitute tension to this one. So what do we get? MAG minus MAA minus MBG equal to that. Which we find equal to, okay, here, equal to MBA. And then we do some algebra work. Okay, what do we get? We can have, okay, so by yourself, we can have the A equal to MA plus MB. Oh, sorry, MA minus MBG. Okay, so it's MB. Yeah, we have, it's 4, 2, 4, 2. So 4 minus 2 is 2, 4 plus 2 is 6. So we find acceleration is one third of the gravitational acceleration. So we get the acceleration, right? We get acceleration. Again, acceleration. Okay, I think we can solve this problem. So, okay. So finally, when A and B reach the same height, we just write down the equation of motion for A and B. Okay. Okay. So let's start it. Okay. So let's start with, yeah. I need more space. Oh, here. Okay, we write down equation of motion. Okay, so we start equation of motion. Okay, A and B. Okay, A and B and XF A equals to XI A plus V initial velocity of A times T plus 1 over 2 A T square. Okay. Okay, so B we here, the final position of B equal to initial position of B plus initial position of B times T plus 1 over 2 AT squared. Like I said, the initial setup, the velocity of A and B is all 0. So this we can ignore this. And okay, so because they reach the same height, the problem asks A and B, when A and B reach the same height. So reach the same height means the position of A, they reach the same height. That means XFA is equal to XFB. Okay, so that's the meaning of reach the same height. Their final position is the same. So when we add this constraint, so what do we have? We will have the equation like this: xi a plus 1 over 2 at squared equal to xi b plus 1 over 2 at squared. Right? Do I did a correct thing? Looks like what is a it's a kind of strange. Okay, let me check. What? Sorry. I understand. Okay, I make a very serious mistake. Yeah, like I say, the direction of acceleration is very important. Okay, be careful. Here, acceleration. Okay, this is one because A moving downward. A moving downward, so its acceleration is minus. Okay, sorry, that's very important. That's very important. So this is minus A. Okay, so the same here. This is minus A. That's so important. Okay, so what's the initial position of A? Initial position of A. Okay, if we set this is 0, this is 0 is here. So initial position of A is 30, and initial position of B is 0. So okay, so this is 30, and minus 1 over 2 at squared. B is 0 plus 1 over 2 at squared. So, and we already know that the A is equal to 1 over 3G. So you put everything together, this gives you at squared equal to 30. And A is 1 over 3G. So you can find the T is equal to, I just give you the answer, 3.03 seconds. So after the initial setup after the initial setup, after 3.03 seconds, A and B will reach the same height. A and B will reach the same height. So this is the application of Newton's second law in combination with the 1D kinematics. So that's why I use the Edwin machine to add as an example. So in this problem, yeah, it's combination of two concepts, Newton's second law and 1D kinematics, and you need to, and these are two object doing motion. So you need to analyze each subsystem. So do first analyze on A, also analyze on B, and give you equation, and then use the equation to solve the acceleration, and then put in the kinematic equation to solve the problem. Yeah, that's a very typical Newton's second law. That's the problem. Okay. So, okay, I just stopped the video here. I hope you can understand the Edwin machine. I believe one of your homework is very similar to this, but it's on the double inclined surface. It's much more difficult. So that's why it's a homework. So, okay, I'll start video here. See you next video. Bye bye. G.I. Joe.